Right, so if you've been following along with the alkenes addition reactions that we did before and comparing it to the alkynes addition reactions that we're doing now, you'll notice that we've done halogens, right? So we did Br2 and we did HBr and HCl and all that other stuff with alkynes. We've done hydrogens, we did hydrogenation, but we added in the Lindlar reduction and the dissolving metal reduction. So we got two new reactions there. You'll notice that we've done all of that, but we haven't really done oxygen yet. We haven't added any oxygens to anything. So things like hydroboration, oxymercuration, right? Addition of H plus and H2O, those kinds of things we haven't really talked about. Well, guess what we're talking about in this video? It's exactly that. And what we're going to find is, of course, alkynes are just a little bit different, but in ways that we can understand as long as we kind of know what we're looking at. So we're going to start with hydroboration in this video. I don't know. We'll see how long this video goes. I might add in oxymercuration at the end, or we might get a separate video for that one. But we're going to do hydroboration and oxymercuration as our two ways to add oxygen to alkynes. Hydroboration. What do we know about hydroboration? We know in general that it does syn addition, and we know that it's anti-Markovnikov. So we're going to keep those things in mind as we do this. So if we look at hydroboration with an alkyne, I'm going to use a terminal alkyne for reasons that will become clear shortly. We'll come back and talk about internal alkynes here in a minute. If we were going to do hydroboration, we would expect the hydrogen to end up on the more substituted carbon. Right? So we expect hydrogen on more substituted. And we would expect the boron to end up on the less substituted carbon. And in general, this is true. The only thing that's different about alkynes is that because alkynes you have a primary carbon here and a secondary carbon here, and there's just not that much stuff surrounding them, we need a slightly bigger boron. And so we use these isoamyl groups, which we abbreviate SIA for secondary isoamyl. So we use this instead of BH3, we're going to still have a BH bond, but we're going to add these very bulky large groups. So a SIA group, a SIA group is secondary isoamyl. So how do I want to draw this? I'm going to draw the whole thing. Cia2 borane looks like this. You have a boron atom, it's got a hydrogen over here, but then coming off of it, it's got these two kind of 5 carbon fragments where they're secondary, but they have a whole bunch of stuff around them, right? Like this is just a really big alkyl group. It takes up a lot of space. It has a lot of electrons. It's going to create a lot of steric repulsion, right? So Cia2 borane creates steric repulsion and therefore forces the boron, excuse me, to add to the primary carbon. Okay. We don't really need to know all of this. We just need to recognize that, well, you do need to know all of this, but we need to recognize the important thing here is that we recognize that the Cia group means that when we do this, we're going to get the hydrogen on the secondary carbon and the boron will go on the primary carbon. This is a syn addition. The hydrogen and the boron get added on the same side, and it's anti-Markovnikov. Right? We're going to do this only with a single equivalent of borane, and so this will stop here. Right? So far, this looks fine. We're taking an alkyne, we're reacting it with one equivalent of borane, and we're getting an alkene product. So far, so good. What happens when we oxidize this? Because remember, every hydroboration always has step 1 with the borane, and step 2 we have hydrogen peroxide and sodium hydroxide. And when we do this, we replace the boron with oxygen. And that's exactly what happens. Nothing has changed too much here. We don't have any surprises for you, except that This compound is interesting. This compound is both an alkene and an alcohol, right? This carbon is both things. It has an alcohol attached to it and it is part of an alkene. So we call this an enol, just combining alkene and alcohol, the two suffixes there. So this is an enol, and enols are particularly interesting because enols are not necessarily, well, enols in general are not that stable. Enols have a closely related constitutional isomer that results from the resonance form of their conjugate base. I'm sorry, just real quick. Now we've got resonance forms. We got resonance forms. We got addition reactions. We got stereochemistry. We got SN1, SN2, E2. All of it's all happening this week. It's all coming together. We must be near the end of the semester. I'm getting excited, right? We can see all the stuff that we've learned is kind of coming back to all work together to help us make sense of this stuff. We've got conjugate bases, acid-base stuff. Sorry, I'll shut up for a while now. Okay, so let's draw the conjugate base, right? We can't see the resonance form of the conjugate base if we don't draw the conjugate base. So we have an equilibrium here. We're going to draw the conjugate base of the enol. This is sometimes called the enolate. The most acidic hydrogen in here is the one that's attached to the oxygen, because not only is it attached to the most electronegative atom, it's also resonance stabilized. So now we can draw the resonance form where we make a pi bond here and put that negative charge on the carbon. Okay. So now we have a carbon-oxygen double bond over here. This is still the enolate because it's the same compound. It's just the resonance form of it. Resonance form. But what happens if we draw the conjugate acid of this thing? Let's add a hydrogen 2 here and make this thing neutral again. If we add H plus H plus minus H plus, if we add H plus, what we get is, now we have an aldehyde. So an enol, especially an enol made from a terminal alkyne, is related to the aldehyde, because if we take a H plus off and put an H plus back on, basically we're just transferring the H plus from this oxygen to this carbon over here. We're going through the conjugate base, looking at the resonance form, and then adding the hydrogen over here, because this is the more basic position, right? We can convert an enol to an aldehyde very easily, very quickly. In fact, this happens without us having to do anything. This is called tautomerism. Tautomerism is converting between constitutional isomers by moving one H plus atom. Right, so we're taking the H plus off of this oxygen and we're putting it onto this carbon. By transferring between these two, the enol and the aldehyde are tautomers of each other. Right? These are tautomers. And tautomers are just a special term for a special brand of constitutional isomer. Right? They will always go through this process of lose H plus, draw a resonance form, add H plus. We don't necessarily have to draw out this process every time, what I'm looking for going forward is that if you see an enol as a product, you recognize that that enol could be an aldehyde, or it could be a ketone, right? If we have an internal alkyne and we treat it with ceaborane, H2O2, NaOH, we can predict what will happen here. We'll get a hydrogen, we'll get an oxygen over here. This is still an enol, right? We still have this carbon here that's part of an alkene and attached to an alcohol. Here's our enol. We can draw the tautomer of this. We're going to transfer an H plus. So I'm using this little squiggle to show the H plus is being taken off and then put back on. We're going to transfer that H plus from the oxygen to the carbon through the same process that I drew on the previous slide. And now we get a ketone, right? But these two things, the enol and the ketone, are tautomers of each other, right? So anytime we see an enol, we know that that's just a ketone in disguise, or an aldehyde in disguise if it's an enol that's on a primary carbon like this one, right? A primary carbon will have an aldehyde because there's a hydrogen here, right? So this hydrogen here, right, is still there in the product. So instead of an R group, we have a hydrogen, so it's an aldehyde. If we had an R group in that position, we would make a ketone. The important thing to know here is that anytime we take an alkyne, whether this R group is a hydrogen or a carbon, right? If we do hydroboration of that alkyne, H2O2 NaOH, we will get a carbonyl at that position, right? We'll get a carbonyl at this position because it will go through the enol and then create a ketone, right? Now, if you have an internal alkyne, you will get the ketone at either this position or this position, which is a problem for another day. But if you have an aldehyde, it will be or if you have a terminal alkyne, which I will draw here, same conditions, right? Ceaborane, H2O2, NaOH, you will always get the aldehyde because hydroboration is anti-Markovnikov. So you'll always get the boron, therefore the oxygen on this terminal position, so you'll always get the aldehyde. All right. All right, this has gone on long enough, so I'm going to put oxymercuration in the next video. That will be a very short video because oxymercuration is pretty much the same idea, except the difference between oxymercuration and hydroboration is, does it follow Markovnikov's rule or not? So you can look forward to that one. I will see you there.